On today's episode of Science Scout, we will be looking at something very exciting. Today we are going to talk about a topic that falls outside of general knowledge: the importance of neuromorphic computing. Many of us wonder just how computers and machines can beat us in games like chess, checkers, and tic-tac-toe, or how autonomous vehicles can learn from humans without human-like distractions or cognitive errors. But first, we're going to assess the future importance that this technology will have in the field of neuroscience. Let's go back in time and take a look at the groundwork and events that led to the current state of field. All computer power and advances are built on top of the von Neumann processor architecture, developed in 1945 by John von Neumann and others, and documented in an unfinished report called First Draft of a Report on EDVAC. Ironically, the most impressive technological revolution in history was built on a half-century-old design from an unfinished paper. Neuromorphic computing, also known as neuromorphic engineering, was developed by Carver Mead in 1980s, who described the use of VLSI, which is the process of creating an integrated circuit by combining millions of transistors onto a single chip. This chip contains the electronic analog circuits to mimic neurobiological architectures present in the human nervous system. Since 2008, there has been an explosion of worldwide interest in memristive devices, which are material-based memory devices with the unique property that their resistance can be programmed and subsequently remains stored even if the device loses power. Interest has also grown in device models, their connection to biological synapses, and their use in alternative computing architectures. For example, in 2014, the industry provided a formal introduction to a new approach to computing called AHAH computing, where memory and processing are combined. In December 2020, BrainChip introduced the Akita neuromorphic processor, which they claim uses 90 to 99% less power than conventional CNN-based solutions. This might be one of the first neuromorphic technologies to enter the commercial market, and the potential applications are plentiful. Also, in December 2020, Intel gave an update on their neuromorphic research test chip called Loihai, as well as their Intel Neuromorphic Research Community, INRC, across a wide range of applications including voice command recognition, gesture recognition, image retrieval, optimization and search, and robotics. Loihai has benchmarked 30 to 1,000 times more energy efficient than CPUs and GPUs, and is 100 times faster. But what exactly is the concept of neuromorphic computing? Neuromorphic computers are models that work like a human brain, with the use of neural networks, where every single neuron sends a signal to other neurons independently when the electrical states of the neurons is changed. Thus, this type of computing emulates natural neural networks that exist in biological brains. The information and timing are contained within the signals themselves, and the spiking neural networks stimulate the natural working process via dynamic remapping of synapses among the artificial neurons in response to stimuli. The responses to spikes can be modulated to represent a continuum of values rather than 0 or 1, and hence provide an analog flavor that is close to the way the brain works. However, neuromorphic systems can either be digital or analog, with the part of synapses played by either software or memristors. Memristors are useful for modeling important processes of the brain, such as the ability to both store and transmit information. Another benefit of memristors is that they not only store the value of 0 or 1, but can store a range of values that allow it to mimic the differing connection strengths among various synapses. Changing those weights in artificial synapses and neuromorphic computing is one way to allow the brain-based systems to learn. These neural networks save energy by working only when spiked, so they don't continually consume energy. Because one synapse might be connected to 10,000 others, that means the brain can transfer information quickly and efficiently. The spiking neural networks can convey information in the same temporal and spatial ways that the brain can, and the networks can use probabilistic computing, which creates algorithmic approaches to dealing with the uncertainty, ambiguity, and contradiction in the natural world. This type of computing involves combining different artificial neurons. The artificial components mimic living neurons with regard to the transmission of information, which electrically pulse only when a complex circuit has a synapse which absorbs enough charge to produce an electrical spike. It therefore mirrors how the human brain works, where there are dynamic exchanges between the over 100 billion neurons and various neuromodulators that change form according to the specific function the brain has to perform. Neuromorphic computers rely on neural network instead of the conventional von Neumann computer. The memory and processing elements in a neural network are located within the same hardware. Neuromorphic computing is a big deal for artificial intelligence, but how does it actually work? As we mentioned before, neuromorphic computers rely on models based on the human brain's neural networks. Artificial neurons aren't of much use on their own, but when you stack them up in layers, they can perform remarkable tasks, such as identifying objects in images and transforming voice audio to text. The DNNs have millions of neurons that are spread in many layers. The simplest version of an artificial neural network based on Rosenblatt's perceptron has 3 layers of neurons, which are the core processing units of the network. For example, let's construct a neural network that differentiates between a square, a circle, and a triangle. The first layer is the input layer, which receives the input values. The outputs of the first layer of neurons, which predict our final output, are connected to a middle layer, called the hidden layer, which performs most of the computations required by our network. The outputs of these hidden neurons are then connected to the final output layer. Here's an image of a circle. This image is composed of 28 by 28 pixels, which makes up 784 pixels. Each pixel is fed as input to each neuron of the first layer. Neurons in each layer are connected to neurons of the next layer through channels, and each of these channels is assigned a numerical value known as weight. The inputs are multiplied by the corresponding weights, and their sum is sent as input to the neurons in the hidden layer. Each of these neurons is associated with a numerical value called the bias, added to the input sum of this value, and then passed through a threshold function called the activation function. The result of the activation function determines whether the particular neuron will get activated. An activated neuron transmits data to the neurons on the next layer through the channels, and in this manner, the data is propagated through the network. This process is known as forward propagation. In the output layer, the neuron with the highest value fires and determines the output, so all the values are probable. Let's take a look at our example. Here, our near unassociated with square has the highest probability, hence the output predicted by the neural network, of course. Just by looking at it, we know our neural network has made an incorrect prediction. But how does the network figure this out? Note that our network is yet to be trained during this training process along with the input in our network. Additionally, as the output is fed to it, the predicted output is compared against the actual output to compute the error in prediction. The magnitude of the error indicates how incorrect we are. The sign suggests if our predicted values are higher or lower than expected, while the arrows here give an indication of the direction and magnitude of change. To reduce the error, this information is then transferred backward through our network via a process known as backpropagation. Based on this information, the weights are adjusted. This cycle of forward propagation and backpropagation is iteratively performed with multiple inputs, and this process continues until our weights are assigned such that the network can predict the shapes correctly most of the time, bringing our training process to an end. But how much energy do supercomputers and neuromorphic chips consume compared to the human brain? Neuromorphic computing is a much better candidate for next-gen computation. Over the last decade, a plethora of private companies and institutions have been working on improving neuromorphic computing. Take, for example, Intel, which developed a Loy-Hi chip containing around 130,000 neurons. Another great example is IBM's True North chip, the first neuromorphic chip in world that becomes non-fundamental architecture. The True North chip has 4,096 cores, each of which contains 256 numerals that implement 1 million spiking neurons, as well as 256 million synapses with 5.5 billion transistors on each synapse. True North and Loy-Hi chips consume only 45 picojoules and 24 picojoules per synapse, respectively, so 1 picojoule equals 10 to the power of minus 12, with a typical power draw of 70 milliwatts. As impressive as this system is, if scaled up to the size of the human brain, it is still about 10,000 times too power intensive. Now, this is still a relatively new concept of computing. The human brain typically contains around 87 billion neurons. each of which synapses with 10 to 15 others, and each synapse consumes approximately about 2 femtojoules, so 1 femtojoule equals 10 to the power of minus 15. When we perform a computational task, we only use a tiny fraction of our entire neuron count. This is the exact reason why the human brain is extremely energy efficient. We consume 20 watts of power, and we are capable of achieving 1 exaflop. An exaflop is 1 quintillion, 10 to the power of 18, floating point operations per second, or 1,000 petaflops. In order to better appreciate this fact, let's put this into perspective. The world's fastest supercomputer, IBM Summit, consumes 30 megawatts of power and is capable of 200 petaflops, while the human brain consumes 20 watts of power and is capable of 1 time exaflops. That means that the brain has 5 times the computational capacity of IBM Summit. Impressive! If we compare the performance of biological neurons and neuron equivalents built from typical CMOS transistors currently used in computers, the differences are so large that it is clear that new scientific advances are needed, including updates of the system's architecture itself. Of course, the silicone device has some advantages over human brain, but overall, system computational capabilities, namely fault tolerance, energy consumption, and ability to deal with large datasets, is considerably superior in biological brains at this time. In addition, these recent technologies have introduced new types of problems that conventional computational systems will never be able to address, even under the most optimistic scenarios. Some of the advantages of biological neurons over silicone neurons is potential differences or voltage. Biological neurons are 10 times greater than silicone ones in this respect, or 0.1 volts and 1 volt respectively. Also, biological neurons have 5,000-fold advantage when it comes to synaptic optic energy, 2FJ and 10PJ respectively, and for total energy, biological neurons have a whopping 100,000 time advantage, 1,000 for silicone neuron. Neuromorphic chips used to power neuromorphic computers may not replace conventional computational chips such as CPU, GPU, or application-specific ICs. However, neuromorphic computers have the ability to add the existing computers that perform deep learning for artificial intelligence. While modern-day computers can do many things that humans can do, they are still lacking in at least 2 aspects, namely, machine reasoning and transfer learning. Transfer learning refers to the ability to transfer or apply learned experiences from one context to another. There is a third angle to consider, which is physical dimensions and energy consumption. Supercomputers represent the highest computing speeds value, and the current versions have speed in petaflops, 10 to the power of 15, floating point operations per second. But these are bulky devices housed in dedicated buildings, and they need power in MW. Comparatively, the human brain consumes about 20 watts of power. Another fascinating avenue of inquiry is what impact neuromorphic computing will have on space operations. Space missions require high-performance, reliable computing platforms that meet size, weight, and power constraints and can function in challenging environmental and operational conditions, including extreme temperature, high radiation, power loss, and disrupted communications. Deep neural net and neuromorphic processors can enable a spacecraft to sense, adapt, act, and potentially learn from its experiences and from the unknown environment without needing a ground mission operations team. For example, object identification and change detection, real-time change detection of information, images, texts, voice signals, currently involves processing, filtering, and extracting massive amounts of continuously received data to interpret events and activities. While these activities have accomplished using von Neumann architecture, neuromorphic computers, NC, could enable more efficient on-orbit data processing and storage by reducing the number of bytes required to save an image and/or eliminating the need to transfer large amounts of data to a ground station for image processing. The current state-of-the-art SOA for in-space processing is the High-Performance Spaceflight Computing, HPSC, processor being developed by Boeing for NASA Goddard Space Flight Center, GSFC. The HPSC, called the chiplet, contains 8 high-performance, general-purpose processing cores in a dual-quad configuration, 8-ARM Cortex-853, which means that single Cortex A53 core manages 2 Cortex R52 real-time cores, ARM, Volt-8 64-bit, with up to 800 MHz frequency. The highest computational capability required by current typical space missions is 35 to 70 gigaflops, billion floating point operations per second. The current SOA does not address the capabilities required for artificial intelligence and machine inferencing and learning applications in the space environment. These applications require significant amounts of computations, in addition to a substantial amount of memory to store data and retain intermediate states in a neural network computation. Terrestrially, these operations require general-purpose graphics processing units, GP or GPUs, which are capable of teraflop, 1 trillion floating point operations per second, approximately 3 orders of magnitude above the anticipated capabilities of the HPSC. However, neuromorphic processing offers the potential to bridge this gap through novel hardware approaches. Neuromorphic processors to be up to 1,000 times more energy efficient than GP or GPUs in artificial intelligence applications. Finally, what is the market value for NCs as well as the latest industry applications? The market for neuromorphic computing is driven by the increasing demand in artificial intelligence and for brain chips which are being used in cognitive and brain robots. According to the report on Sheer Analytics and Insights, the global market of neuromorphic computing in 2020 was 20.9 million and is expected to grow at a CAGR growth rate of 50.3% by the year 2028. According to MarketWatch, global neuromorphic computing market will reach $8.9 billion USD by 2025. Global neuromorphic computing market was valued at approximately 1.6 USD billion in 2016 and is anticipated to grow at a healthy rate of more than 21% over the forecast period of 2017 to 2025. Neuromorphic computing is currently used in different industries like aerospace and defense, medicine, industrial uses, automotive and IT, and telecom. For example, neural-inspired computers are explored in areas like self-driving cars, classifying vapors, or even identifying an individual's face out of a lot of random images. For instance, Intel's Loihi chips are being tested by researchers, including at the Telluride Neuromorphic Condition Engineering Workshop, for their use in the creation of artificial skin and in the development of powered prosthetic limbs. IBM also recently announced its partnership with the U.S. Air Force Research Lab, which they are creating a new neuromorphic supercomputer called as Blue Raven. They are exploring its uses for creating smart, lightweight, and more energy-efficient drones. As we see, neuromorphic-inspired architectures are being developed to address the shortcomings of modern computing to meet next-generation electronics requirements. Deploying faster, smarter, autonomous, and more power-efficient computing is a significant advantage for governments and commercial stakeholders alike. It's been an interesting ride today learning about neuromorphic computing, and I hope you enjoyed it as much as we did. Let us know your thoughts concerning this unique type of computers.